For section 3 of chapter 12, we're looking at two main concepts here. One is multiplying two vectors together, and the other is the idea of parallel and perpendicular vectors and what that would tell you and how to work with those within a few problems. So first things first, if we were talking about multiplying two vectors, they refer to this as the dot product of two vectors. And so if I'm going to multiply vector v times vector w, you simply multiply their common components and then add them up. And so I would multiply the horizontal components together, a times c. I would multiply the vertical components together, b times d, and then add those two results. So here's the look that you get, and that gets their dot product. So if you're to do that with a three-dimensional, it's the exact same thing. So you just multiply the common components together and then add the results to get your dot product. So a couple examples that you're seeing right here for part C. So again, I'm going to multiply negative 3 times 4 plus 7 times negative 1. And that's the look that you're getting over here. And negative 19 would be the product of those two vectors. And then same thing right here if you want to give number 2 a try. Same concept, but with 3 dimensions instead of 2. From this, we develop a formula for getting the angle between two vectors. And so here is sort of the original format of the formula. And you'll be looking at your formula packet for this concept here. But this is the original formatting. But typically, we're trying to figure out what the angle is. And so if I want to isolate this, then I'm going to divide these magnitudes over to the left. And so here's the look that we commonly deal with, is this look right here. And so you have the dot product on top. On bottom, you're multiplying this magnitude times this magnitude. And then if I do the inverse cosine, I get the angle between them. And so here's a good look at how that would look like over here. So if we're going to try that with some real numbers, here's a few examples. After the first one, you might want to pause and try the second one on your own. But with the two-dimensional, again, you have the dot product on top that we covered in the first part of these notes. On bottom, you have the magnitude of v times the magnitude of w. And so if you do a little cleanup on that, we get it over to here, a little more cleanup. Notice at the end of all this, of course, you would throw this into your calculator and then do the inverse cosine to get the angle between them, which is about 53 degrees. Exact same concept right here for number 2. So if you want to pause and give this one a try, same deal, but with 3 dimensionals. So again, you got the dot products on top. You have magnitude times magnitude on bottom, and then inverse cosine at the end to get the angle between the vectors. And so that's the first half of these notes, just dealing with dot products and the angle between two vectors. Link this into this idea here for perpendicular and parallel. So keep this formula in mind, because everything that we're going to talk about here for perpendicular and parallel stem from that formula. Let's see if I can try to keep all that in the screen here while I'm talking. But if you look at this example, if I had these two vectors, and if I were to go through the same formula that we were just covering, well, notice what you would get from the dot product on top. If I get negative 3 plus 3, that equals 0. And 0 divided by anything is 0. Well, the inverse cosine of 0 is 90 degrees, which simply means I have perpendicular vectors. And so the simple concept that you need to get out of this is this number is irrelevant. Anytime the dot product is 0, I have perpendicular vectors. And so that's something you really want to take note of. So again, dot product is 0, perpendicular vectors. And so here's the rule right there for perpendicular vectors. You'll see this again down below. But if you look at part B of this, similar concept, but now with parallel instead of perpendicular. Look what happens for parallel vectors. You'll notice that you're getting the same number for the dot product as you got when you multiplied the two magnitudes together. So obviously if I clean that up, I just get a value of 1. Well, the angle where you have a cosine of 1 is 0 degrees. So that would tell you that there's no angle between them which means you have parallel lines. If it is 0, that means you have parallel vectors running the same direction. If you get a look like this one that you're going to see here, where I had negative 30 over positive 30, well, if you clean that up, you get negative 1. Well, what's the inverse cosine of negative 1? That's 180 degrees, which means you still have a straight line. They're just not running the same direction. But when it comes to vectors, they do not have to run the same direction to be parallel. So even these vectors right here are still considered parallel vectors, even though they're running opposite directions. So that's this idea here. So whenever you get the 180, that just means they're running different directions, but they are still parallel. So anytime, again, that you get the look where you either get a positive 1 or a negative 1 out of all that, you're going to get parallel vectors. The thing that you really want to note about parallel vectors, because there's an easier way to figure out if vectors are parallel than what we just did right here. And you're going to see this in the upcoming notes. Notice the numbers here and here. If you notice that this is a scalar multiple of this, that's the easiest way to figure out that the vectors are parallel, and I can do that without any of this work if I notice that these are a scalar multiple of these. If I multiply vector v times negative 3, I get vector w, so this is a scalar multiple, which means the vectors are parallel. And that's the easiest way to determine whether they're parallel. This works too, and this is the mathematical way of figuring that out, but there is a way of figuring it out with scalars as well. So look at a couple more examples of that with me down here. But again, this was the rule. So anytime the dot product, this was the number on top, was equal to the product of the magnitudes, this was the number on bottom, anytime those are equal, whether it's positive or negative relationship, you get parallel vectors. So common questions that you're going to see right here for parallel, perpendicular, or neither. Again, just use the rules up above. If their dot product is 0, we know that they are perpendicular. And so that's what you would have noticed right here on number 2. I just checked the dot products. I get a 0, so it doesn't even matter what number's on bottom, because 0 divided by anything is still 0. So I know that these are perpendicular, and I can just figure that out with the dot product. But if it's not 0, then it could either be parallel or neither, and so I got to determine which one of these I have. So notice for this one, we just started with the dot product, figured out that it's not 0, so these are not perpendicular, so now I'm checking, okay, well, are they parallel or are they neither? And there's two ways to determine this. The longer way is with the formula. Here's what we would have on bottom. So if I did the magnitude of v times the magnitude of w, and that's the work that you're seeing right here, well, their magnitude times magnitude is 180. So if I did the formula for cosine, I have 180 over 180, which is 1. So if I did an inverse cosine of 1, I get 0, which means the lines are parallel. And that's the way you figure it out with a cosine formula. But again, you might have noticed that vector w is a scalar multiple of vector v. If you're not sure, because this was not as clear, those numbers are not as obvious, just do some ratio testing. Is negative 4 divided by negative 6 the same as 10 divided by 15, the same as 2 divided by 3? If I get the same answer every time, then this is a scalar multiple of vector v. And so you could have figured it out that way as well. And that, well, I'll get to that here in just a second. But if you look at part E here where it says find y such that a and b are perpendicular, again, your keyword here is perpendicular. We know from the rules up above that if the vectors are perpendicular, then their dot product is 0. And I don't have to do the full cosine formula to figure this out. I'm simply checking the dot product for perpendiculars. So perpendicular dot product is 0. So if I did 4 times 2 plus negative 3 times y plus 1 times negative 5 and set that equal to 0, I can solve that simple equation for y and figure out what y would have to be in order to make those guys perpendicular. So again, the key idea on that is just setting the dot product equal to 0. If they're parallel, well, again, the easiest way to figure this out, and you don't need the cosine formula to do this, the easiest way to deal with parallel vectors is scalar multiples. So I need to know what would my scalar be in order for that to work out. So if you look at this, just set up a proportion. So I would just do something like, well, x divided by 8 would have to equal 10 divided by -4. And if I just set up that proportion, I can cross multiply and solve for x. There's more than one proportion you could set up here. So there's more than one way to get this answer. You're seeing all three ratios right here. But we only need two ratios to make a proportion. So I could either do what I just said in the beginning, or I could have done x over 8 is equal to -5 over 2, and that would be another proportion that I could use to solve for x. Last one here, part G, again, keyword here is perpendicular. These are definite like test IB style questions right here, so these are definitely ones you want to be familiar with. But as soon as I see the word perpendicular, I know that their dot product would equal 0. And so that's like your key right there to set it up the problem. This one's a little more complicated in solving, but still very doable here. So just dot product is 0. So I know that I'm going to do this component times this component plus this times this plus c plus 2 times -4. I'm going to add those three together, set it equal to 0 because they're perpendicular. So that's the work that you're seeing laid out over here on the right. So you have the first components plus the second components plus the third components, all that equals 0. And now we just go on ahead and solve for c. So this one we did solve a quadratic, so you got the two solutions. You can always check by plugging those back in to make sure that they fit.